Ørsted showed us that a current can make a magnetic field. So what we're going to do is look at a few geometries of magnetic fields created by currents, just to get a feel for what they look like. We're not doing the equations yet. That's for later. Right now, let's just see what happens. So first, let's look at a long, straight wire. And when I'm talking about wires in this section, it's implied that they have a current flowing through them. I'm not going to write out carrying a current every time. So a wire, and of course, it's carrying a current, because that's the whole point. Okay? So here is the wire. It's got a current flowing through it like that. So if you have a long straight wire with a current, then the magnetic field just makes loops around the wire. Little cylindrical field forms like this. And it goes from behind the wire up to in front of the wire down when the current flows in that direction. One more. Ooh, okay. Yeah, and that like that. So you can see why it caused the the compass's needle to turn. If we had the compass here and say north, it's off like that, the needle is pointing like that for the Earth's magnetic field. As soon as we turned on the current, the needle moved because it was being pushed by this magnetic field. We created a field much larger than the Earth's magnetic field. And that's how it was first discovered by Ørsted. But the visualization, or the way the field would look, if you were to look at it, is it's cylindrical lines, or it's lines going around a cylinder around the wire. Let's look at another one. Let's look at a wire loop. Okay, so just a little circle of wire, of course, with current going around it. So let's see if we draw it kind of like this. So there's the loop, the current is going around like that. This is the back and this is the front, kind of looking down on it. This will make a magnetic field that goes up like that. It goes through the loop. And when you get off to the side, it kind of starts to curve out like that a little bit. And it might kind of go like that. And it might kind of come, oops, it might kind of come like that. Okay? So it just makes a field that kind of goes through the loop, and then it actually comes back around to itself. Okay? So that's the current. These are the field. And actually, it matches the wire case. If you look at it and you say, well, right around the wire, it needs to circulate around the wire, and it does. See, this is going around this wire carrying current. This one is going around this wire carrying current. But in the middle of the loop, the part you care about, it's a way to make kind of a uniform field, a field all pointing in one direction. Later, if we stack up a bunch of loops, then it makes a really uniform field. It makes a solenoid. Okay. We can also then, now that we sort of understand that, we can think about a magnetic material. So remember, we had the bar magnet, and it had a north and south pole, and it made a field that kind of went from north to south. But now we can actually understand what's happening. Why is the bar magnet doing that? It's because it's filled with microscopic current loops. The little atoms inside the magnet make little current loops going around. And in most materials, all these little current loops, due to the atomic orbitals and the electron spins, they all kind of just cancel out. But in some materials, they don't cancel out. They line up, and they give you a big magnetic field. Now, to make it match this, you've got to see that inside the magnet, this is confusing. When you think of a bar magnet, the field goes from north to south. But inside that bar magnet, there's a big field adding up, going from south to north. Because just like this current loop, if the current's going around like that, the field comes from the bottom up and it goes around. So you can see a bar magnet, or a magnet material, a magnetized material, is just millions of teeny, teeny current loops adding up. And the magnetic field we experience is the outside the loop magnetic field. Okay? So a current loop is actually very fundamental. So when we think about magnetism, a current loop is so fundamental, it gets its own special name. It's called a magnetic dipole moment. So So let's think about that for a minute. First of all, why is a loop fundamental? You think if something's fundamental, it's a line of charge. When we think of what is sort of the fundamental thing that gives you magnetism, you want like an isolated little small thing. So this can't be an isolated thing. This is an infinite wire. The current had to start somewhere, the current has to go somewhere. There's no way to make this a thing. The only way to make it a thing is to make a loop. So here's something little that we can hold in our hand. Right? You can't hold an infinite wire in your hand. But when you take a current that has to flow and you make it go in a loop, now that's sort of a thing. Okay? And now you can start to see when it flows, when current flows through this loop, that sort of one side of the loop is the north pole and the other side of the loop is the south pole. And that's why when they line up, we call them the north and the south pole. That's why it's a dipole moment. A monopole would be a charge. In electrostatics and electricity, we have charges that generate the field. In magnetism, it's always these loops. And this is why you can't ever separate them. This is why you always have to have a north pole and a south pole, because there's no way to cut this in half and just get the top or the bottom. There's always a top, there's always a bottom. Even if you cut this wire in half, you'd have two wires, two loops, just like before when we talked about cutting the magnet in half. Okay. So mathematically, the magnetic dipole moment has a name. It's mu equals I times A. So the magnetic dipole moment is a vector called mu, and it's simply equal to the current flowing around the loop times the area of the loop. And it's that area vector we're familiar with where you pick a direction, or where there's a direction for the area vector that's normal to the loop. Okay? So mu equals I times A. So usually we don't draw it quite so fancy. We could just draw a loop like this with the direction going like that, the current going like that, and mu sticks up like that, just like the area vector would. So we're going to use mu when we think about how things interact with magnetic fields. But it is the fundamental magnetic source, is a magnetic dipole moment.